Hi, everybody. I am sorry I'm a little bit late. It seems like I'm having trouble with my internet. Um, yeah, even the speed test doesn't quite work. So is everybody able to get the exam that I sent out?
Hold it up, yes.
Yep. And that's funny because I bought like a brand new modem today because there's just too many people using it in the house, or a new Wi-Fi router. Thought I had checked it out hours ago, and I don't think that's the problem. All right. So it's a little bit hard to do it the way we traditionally do it, but I can give you like 10 minutes. And then if you're having trouble with question one, you can just chat me your question. And then every 10 minutes, I'll just do a solution. How's that with everybody? Or does anybody have a problem with that? All right, I have one sounds good. Okay. Two sounds good, makes it official. All right. Actually, I wanted to just talk a little bit about the exam structure before we get started. You can just hear me in the background. So, in structure, right, it's gonna be just like the homework. You download the exam at the proper time, right? And then you either do it on some kind of electronic device, or you print it out and do it, or you just kind of write your answers on a piece of paper, right? But everything's got to be legible. Everything's got to be, I guess what I'm saying is when you put everything together, right, you got to have everything in order, everything oriented the same way, just like the homework. And I will give, so normal exams are 75, and then we'll give plus 15 just to upload it, okay? And that'll be, so the assignment will open, you'll be able to download it and close. Come 15 minutes early, right? And what I'll do is, just turn on your camera, and then as I call your name, you'll say present and you'll hold your ID up to the camera. And what that'll do is you will jump to the forefront. I can see your ID, and then I'll move on and take attendance. If you don't have your student ID, just use some kind of picture ID that you have. All right. And then as soon as we're done taking attendance, we can take the exam. There's also the honor quiz. You need to do that ahead of time. All right. Research has shown making an honor pledge not to cheat is a very cost-effective way to reduce cheating. All right, so like I said before, it's open book, note, some like to say internet, right? But no help from a person, living or dead, no Ouija boards. I don't think AI is good enough to help yet, but you never know. And then, what I would do though is make your own equation sheet, right, ahead of time. You can use mine, whatever, but when you don't assume that since all the information is there, that you'll be able to easily access it in a certain amount of time, right? Open book, open note can lend you to a false sense of security. If your Roomba can help you, we are in serious trouble for our careers. Any questions on just that bit? Just kind of the mechanics. It's all in the website, or it's all in Canvas under, online exam protocol. All right. And we piloted this in 98 and it seemed to go pretty smoothly. And if you're having a trouble, just email me. And sometimes things just die, and that we'll just have to do a makeup. What is the honor quiz? All right. Let's go check out the honor quiz. But it's an assignment, it's a quiz, and you got to answer it. So we should be able to find it. Maybe I didn't give it a due date, and that's why it didn't pop up. Yeah, that's the problem. So now it's due. All right. It should now pop up on your calendars. Yeah, listen, there is a thing called private chat, which I'll turn off during the exam. But if you're talking to a friend, like something like what I missed, maybe you could do a private chat. All right. Because I'm looking at these chats as like questions, right? All right. Um, all right. So we kind of, that kind of burned the first 10 minutes of the question. So what I'll do is I'll go over the answer of the first one as if you were studying the whole time, as if you were doing it the whole time. Just get this away. You should have gotten an email where the sample exam is, but it's also under today's class. Module 22, midterm S20 practice. Okay. I actually, this is just practice. So I had sent out that email a half hour ago. Okay. The real exam, you won't be able to, it'll be, that's a good question though. The real exam will be right up here. Okay. And maybe it's better to call this honor policy quiz, where you look into the camera and it sees your soul. All right. Anyway, everything's recorded. Although that one lecture, Zoom still hasn't gotten back to me yet. So we have a fourth order. All right. Basically, you have the camera on, but you're not looking at it. It's just on. All right. That way we can just do the best of our ability to make sure you're not receiving outside help. Okay. All right. So let's make this into a DF2 circuit. It's fourth order. So that's really going to be 4 integrators. Now, yeah, to convert it into integrators, now I have it memorized. I divide by the highest order of S, which is 4, which will now transform equation into this. S squared, S cubed, S fourth. And we're going to share these so we need 4 integrators. All right. So it's just best to draw them out. I like to start with the RCs first. Four pairs of RC. Four op amps. Part of the reason why I like to draw it kind of in this, it's almost like I'm drawing it like it's an algorithm. And that way it prevents me from making silly mistakes. So there are the integrators, right? 1 over s, 1 over s squared, 1 over s cubed, 1 over s quadrupled. Then we want to do the summer. This is in, and we'll call that Rn. Now, I'm just going to go over the answer. I'm not going to like really derive it, okay? But here's integrator 1, and that constant A1 is set by R1C2. And it's negative, right? And we want to keep it negative because this is all negative feedback. So negative into the positive side keeps it positive. But now this is depending on R2, C2, R1, C1, but it's positive. We need negative feedback. So we have to bring it into the inverting side. All right. We need to balance it. Okay. This all needs to be balanced. So we have one, and this assumes that all the A's are done here so that they don't need any scaling and that all these resistances will be the same. I have 1, 2, 3 inputs, right? I have 1, 2 inputs. So to balance it, I just need one of these. Now, in the past, we've had high and low pass and then notch, right? And this is I think it's a band pass. Just let me see what I said in that question. Yeah, band pass. Okay. But so here's the thing. These, oops. So we usually had S cubed or something, and whatever that was the output. But the B's are the outputs, and there's 3. So we need to sum 3 things. This filter needs a sum, and I'll tell you, okay? So basically, I'm taking out 1, 2, 3 equations, right? Something that with no integrator, something with 2 integrators, and something with 4 integrators, all right? So this one does need an output summer, and I'm just going to draw the basic structure of it, all right? And I'm going to switch colors here. So this, right, is actually B0, and it's just scaled to 1. but it has no integrator. This has no integrator.
Oh.
So I'm going to bring it here, right? And that's going to be our B0. Now then we have something coming out of two integrators. 1, 2. All right. And on the B networks, we want positive. Everything needs to be positive. Here, everything needs to be negative. Here, everything needs to be positive. So if it's already positive, we keep it positive. And then the last one is something with 4 integrators. All right. So now to balance this, we have 1, 2, 3 inputs to. Now really, you can use one resistor to balance all of these, or you could just draw that. All right, but really, you only need one at the proper value. And then, now it might seem that it's obvious that's out, but then you need to label that out. No need to come up with the values. But yeah, you need 4 inverting integrators. They need to be summed back properly. Sometimes people bring the feedback to one of these nodes where no, it's either coming in on the negative node or it comes in on the positive node. And a voltage can't just connect to a line or a node, it's got to connect through a voltage. All right, so now myself, yeah, I can look at this equation and just draw it out, right? But this shows the thought process. Other key points are negative, 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 positive, positive, right? Tied to ground and things like that. Okay. All right, I'll give you a few minutes to work on the next one. And here's the thing, even if class goes longer and you have to leave, I'll just keep answering. I'll just solve it, right? And then you can watch it on the video later. Oh yeah, what's your question on 1? But everybody else can keep working on number 2. Didn't have feedback on the output summer. The way this works is that the B's, they're just summed. There's no feedback. Only the A's are fed back. That's just, if you derive how this transfer function works out, right, that's what would happen. But B's don't get feedback. Yeah, there's just no, the rule is there isn't any. You could call it, like when somebody wants to use the word feed in terms of the B constants or the output summary, they call it feed forward. Right? You're just feeding it forward. You're never feeding it back. Okay, good question though. All right, that's been, I think, 5 minutes. So what we have here is the damper, right, which is the resistor. We have the spring, which is the inductor, and here is the mass, which is the capacitor. Now what we've got here, right, is this kind of rigid body that's connected here and here, almost like you're in an elevator and you're touching both sides. And so that the Vx is here is the same, would be Vx here. And that's really like a voltage source, right? That's just connected to two different things. Okay. That would be R, and that would be L. Now, the thing about the mass is that one end is always connected to ground because Vy is nodal. Vc, voltage across the capacitor, right, is device and represents the velocity. But the nodal has to be with respect to ground. So this Vy, the movement has to be measured with respect to something that's not moving, right? And then you can see that, yeah, the input is connected to one end of the damper, one end of the inductor, and then they're both connected to the mass. Now the thing is that that might be physical, and you might say, well, one is attached to one side and one is attached to the other. But really, if everything is rigid, right, I could redraw this, right, damper here, and it would, and get rid of it there. It's mathematically the same thing. This mass really doesn't have dimension mathematically. Okay. So transfer function is Vy over Vx, which is going to be the impedance of a capacitor right. This is going to be Rs divided by R plus Sn C C. Okay. So multiply through, I'll just draw it. Multiplying through S squared RLC plus 1 find now it's true you could find out whether it's over critically or under damped from right here, but it is better to pull everything out. But you can actually leave this if you like, because this will tell you over under critical. Any questions on that? I think while you're thinking of a question, I think the hardest part is to think that the mass, one end of it is always tied to ground, because you can have, I'm going to have a damper, and I can have a mass, if that's my Vx, my velocity, and I'm calling this fixed, oops, I meant to put an inductor in here, or a spring, right? That mass already has one end connected. This inductor is connected to the mass and a ground, right? But you actually see the inductor connected to the ground.
Professor?
Yes, sir.
So that would that be the block with the lines through it? Would that be considered a moving surface? Like it's
when you see Vx, that's moving.
Okay.
This means fixed, and I'll say it. It's you'll see it in the questions that I've asked. It'll say fixed.
Okay, thanks.
Now, I just thought of a new question. is that, let's say I had a mass, right? And I had Vx, right? So that means this platform is moving at a spring. And I called this Vz, and that was moving. And this is V.
Can't find the key still?
Y. Well, that's actually two input voltages, right? And I would have the mass is still tied here, right? An inductor would come here, and I would have Vz. And this would have Vx. And you could use superposition to solve it, if you like. I don't know if I might have heard a question, or maybe that someone was just dealing with something at home. Okay. So that's 1, 2. And basically we have an op-amp model in a non-inverting gain stage, and just find algebraically where that'll actually work like it was an ideal op-amp. I can go back here. So you can just see what I was doing. All right. Give you, I know it might not be enough time, but I'll give you 5 minutes to contemplate this question. Alrighty. So in this case, we're going to do it algebraically, but we could, oh, I didn't see your chat there, so just a second. All right, any ideas? I would look at the homework solutions. So basically, let's just draw our signal flow diagram. The summer is right here. It's the op amp. But, actually, I'll draw it the way it's oriented here, right? So here is our in, right? What's inside that is this transfer function. Which, we might call HS of the op amp. There's our output. And then we would have a GS feedback function being subtracted. All right. Well, what is GS? Well, if you look here, I minus equals 0. And so if we call that Vx, right, and that's V out, let me just draw it in an easier way to see. Well, you can see it's a voltage division. Which there's no function of S, so we just call it like beta. All right. This is kind of our standard one loop feedback equation that I tend to just have memorized. Okay. When you multiply through the denominator, you see that it's 1. I'm just going to, so this is just replicated. So we get S plus 1, S plus 1 meg, right? Then this cancels that, and I'm left with beta AV. All right. Now I try to put it in the proper polynomial form. S times S is S squared. 1 times 1 meg is 1 meg plus beta AV. And then here I have 1 meg plus 1, which you can put here. Now really, this is your A, which is 1. This is your B term, and this is your C term. And depending on what AV is and what beta is, you can determine whether your system, in this case, since it's second order, is over, under, or critically damped, right? This question though is when will this act like an ideal op amp? Well, you really want, if AV went to infinity, right, it would carry the beta along with it and drown everything out. And then I'd have AV divided by AV with that beta term. So really, what's infinity? It just being bigger than that. So beta AV just has to be much, much greater than, and I'm just going to put here the magnitude of this. And then that'll ensure that it'll work, right? If that is true, right, I get AV beta, which will eventually lead to this, which this problem's pretty much worked right out in the notes, line for line. All right. Anyway, you can go back and look at those. So actually, I'll just ask it straight out. You know, anybody can either chat the answer or shout it out. But what is making this system not be in control? All right. We have positive roots poles on the right-hand side. Okay. You can look at the chat for the answer. Now, rather than actually calculating it out, I know there's got to be some there because the S term is missing, right? And minus 100. Signs not all the same, okay? So, which, yeah, what does that all lead to? Poles on right-hand side, right, which leads to e to the plus t, all right? Now, if it's right on zero, right, if you could have purely complex poles, right, and then you're going to get an oscillation. Okay. We don't have to ignore anything. It's good to try. So thing is I know that I need to turn, by looking at it this way rather than maybe another way, like what's wrong with it? Not what the poles are, but what should the shape be, or, right? And so I need an S, right? And I need a positive 100 or something. All right. So we're going to apply, here's our h of s. What g of s is going to fix that for us. All right. So h of s multiply everything through. Oops. So we have to have something in GS that can turn this positive, because now there is something there, right? So we need something to turn it positive, and then we need something to turn this positive. And so since there's not everything's the same, is multiplied by the same order of S, there's going to be two parts to it, right? There's going to be maybe K1, right? Because if I multiply K1 times minus 10, and K1 is negative, I can turn that positive. But if I multiply positive S, but it doesn't get me anything here, I need to get rid of that S so that I can have 100. And so I can use an integrator, call it K2 divided by S. All right. And now what else I have to do is worry about each thing individually, right? So I need K1, right? I need that to be greater than 0. That means K1 just has to be less than 0, just has to be negative. So that condition is all on its own. I don't have to worry about the rest of it. All right. And then over here, I have minus 10s times K2 divided by S, right? Minus 100 has to be greater than 0. The S's cancel, right? K2's got to be negative. Yeah. To see this more fully, I have S squared. Right here I have minus 10S times K1. Here I have minus 100 minus 10S times K2 divided by S. The S's cancel. So I have 10, right? And so I just have to have it less than 10, less than negative 10, and it'll do it. Because we just need this bit positive and this bit positive. All the terms of S are there, and then it'll be stable. I see your chat. I'm just trying to get to it. How did I get it? It's a good question. The answer, because that's what would work. Let me break it down a little further. All right, is that in the feedback equation, Q of S, right? We had S squared minus 100 minus 10S G of S, right? I need some positive number times S, and I need some positive number with this greater than that, so that this becomes positive and that adds that S term. So this, right, I have to pick a GS that makes that happen. And well, what are my options, right? Proportional, derivative, and integral. And yeah, I can even have multiple integrals. So the thing is I have this term, right, which I need to either make positive because that's where my S is coming from. It's already there, right? So to convert this into a positive S, I just have to say, oh, minus 10S times K1, right? So G of S has K1. I'm just seeing that I needed a term of S and I need it positive. So all I have to do is multiply K1 times that. But that doesn't do anything about this negative sign here. So, right, because K2 divided by S, right, the K2 can be negative to turn that positive. The S's cancel out, right? But you can try one like, well, what if I added S plus K3? Well, I get minus 10 S squared K3. Well, I already had S squared and it was already positive. Now, sure, I could turn it negative, right? but it doesn't get me this value here. And so I'm just, in my mind, I'm trying out the various feedback mechanisms to turn whatever's here into the things, the thing or the things I need. Okay. Does that help? Okay, great. Maybe we have to just start on the final question. Okay. So this, this is like kind of a matching game, but it's like logically what's what. That's strange. So what we have are some spectra, right? You take the Fourier, you find the Fourier coefficients, and you convert the A's and B's into magnitudes and phase, right? So here's one where the DC part is a half, and then you see it, there's a constant at every harmonic, and then the phases are all 90. Then here we have something at 0.75, and then we have harmonics that we have one at 1, 2, third harmonic, fourth skips here, and the phase is different. Here we have a DC plus something at 2 kilohertz. Might be a little bit hard to see. When you print it out, you'll be able to see those. And then here we have something with DC, something at 2 kilohertz. Okay, and the phase, this is 1 e to the minus 15. That phase is effectively 0. Well, then we have some periodic signals. All right, the period is 1 millisecond, 1 millisecond, half a millisecond, half a millisecond, right? So you want to try to see which ones are which, right? Now, the way I would probably approach it is, you know, first, are the frequencies right? And so the period here is 1 millisecond, 1 millisecond. So which ones have harmonics at 1 kilohertz, right? Well, the first two. Now, then they have a lot of things. Now, you could, yeah, it's true. You could come up with this function, right? And then try to solve for the Fourier expansion, but it's kind of difficult. But something that you could do is find out what is going to be the DC part. So what's the DC average, right? So what is the average of this signal? Well, the width is 1 millisecond, right? the height is 1 millisecond. It's a triangle, so you're going to get 1/2 the base times the height, but then you got to scale it by the period because we're integrating. And so what you get is a DC offset of 0.5, right? Here, you know that it's not at 0.5, you know that it's not at 0.8, but it goes to 1 and then comes off. And so there's going to be some average, you know, between 0.6 and 0.8, closer to 0.8, where that'll be your DC offset. So if I come back here, right, because you know that things like this have a lot of, you know, they have a lot of higher order harmonics. And so which one's which, right? Well, the first one, right, we said the DC offset was 0.5, and that one's got 0.5. And then the other one, we said it was somewhere between 0.6 and 0.8. Well, there's 0.75. So even if you didn't, you know, solve for that's basically it's the classic shape of a sawtooth, where you've got every frequency, and that's pretty classic, right? Now then, so that sorts out those two. And then here, I look at it and say, well, wait, I'm going from 2 down to 0. So there's going to be an offset, right? Here, I'm going from 0 to 1. So there's an offset. And they're both going to be at 2 kilohertz, right? All right, so unfortunately, right, this has an offset, that has an offset. This has something at 2 kilohertz. This has something at 2 kilohertz. How's that going to work? Well, you can see that this is going from 1 to 0. So the amplitude is, the peak to peak is 1. That means the amplitude is 0.5. Here, the peak to peak is 2. That means the amplitude is 1. And then you can see that it's all going around 1. So the DC offset is 1. Here you can see, it's a little harder to see, but it's centered at 0.5. So there's your 0.5 offset, there's your 0.5 amplitude, 1 amplitude, 1 offset. And yeah, this is really sine squared. This is sine of 2 kilohertz plus 1, right? That's maybe the trick that I was anticipating. All right, we lost a few people. That's okay, they can, I know you got other class. Any questions before we go? I strongly suggest you do this exam on your own without the answers, without even, you know, trying to look anything up, just to see how you do, and then go back and then study what you need to study. Okay. $15 points for submitting. It's 20 points per question. It's either right or it's, 15 minutes extra. Well, yeah, it's 15 minutes extra to digitize your work and submit it. But no, it's graded just like normally, but you'll see all the marks in Canvas, which it's a little clunky to do. So you might just see check marks when it's wrong and a cross out. I mean, check marks if it's right, cross outs if it's incorrect. And you really can't really get the feedback on your phone. You got to log in with a big screen to see that. All right. But no, this, This kind of exam is actually really no different than any other exam we give in 110. But still, good question. Thank you for asking. No, I don't know where that came from. The exam is on Monday, all right? That's what it was on the schedule. What I'm thinking is when I said, yeah, on Wednesday we'll have a practice exam, and maybe the internet cut out and you heard Wednesday exam. But no, it's really Monday. This is the review session. Okay? We really didn't drop any time because I already knew how to teach online. Oh, oh, that's a good thing. Yeah. How about I send out an email? We don't want any confusion. Okay. Actually, everything was in the same order. I didn't have time to mix it up. So 1, 2, 3 is ABC. So there won't be a lecture, right? But you'll have to log in Zoom so that I can check your IDs and make sure you're, not receiving outside help without using an invasive lockdown browser or really invasive uProctor. But I won't record it, just so you know. Nothing's recorded. It's just given the fact that none of you officially signed up for an online course, one cannot really force the issue on lockdown browsers and things like that. But also, doing some research, the companies that sell these tools try to scare professors, right? But professors who have done some research say, like, the most cost-effective thing is the honor quiz. Okay. But yeah, you got to come in Zoom and you got to have your video camera on, right? And yeah, you got to leave your mic on. But if it gets too noisy from your end, yeah, you're just going to have to mute it. And if it's too, I don't know, I guess if I'm being too noisy, I guess you could mute me or just turn your volume down. Don't mute me. I'll be quiet. Yeah, listen, I kind of covered this at the beginning of class and in the online protocol, but it's just like the homework, except in the homework, you have access to the homework the whole time, right? This is when the exam starts, you can download it, print it, do it however, digitize your work however you want, and upload it like a homework. Okay, well, thank you for coming to the review. That is a great summation. It is like taking a timed homework while on Zoom. Yeah. Except on homework, I'd like you to help each other out. On the exam, not so much. Okay? Okay. All right. Feel free to email me. Please stay safe. I still miss you. Hoping to at least see you on campus next fall. I know there's a lot of things in the news about universities planning. But that's what universities do. They've actually got the next 3 years planned out for when classes start and things like that. So, you know, we weren't necessarily prepared for this thing, but, you know, going forward, we should all have a pandemic plan. Okay, take care.